Okay, thank you very much.
All right, thanks. Can you hear me all right? All right, so first of all, thanks a lot for inviting me here, and big thanks to Trevor, M5 AKA, yes. It's my first time here, but it's been great, and it's really getting better by the minute, so that's fantastic. So my name is Aleksander. I'm doing a doctorate at the University of Southampton in the area of space debris. You may think it has nothing to do with CubeSats or amateur satellites or anything whatsoever. In point of fact, it does, but I'm not going to talk about this. What I'm going to talk about instead is the University of Southampton Small Satellite Program, or EOS-CUBE, if you like the fancy name. It's a pretty recent program, but based on some previous work that I've done at the university, but I'm going to talk about it in a minute. So first, what I'm going to tell you is slightly about who we are and what goals we're trying to achieve, and then go to some more specific mission objectives that we set. And then I'm going to talk about the hardware specifics, and as we go through the hardware and software, I'm going to talk about some lessons that we've learned regarding it, because I'm pretty sure that some of you might actually find it interesting and might want to reproduce something that we've done. So it's probably going to be useful for you guys to know, what things to look out for and so on. Right, but there you go. So first, the boring bit. So what we're actually doing at the university is we're educating, and this is the primary goal that we've got. And we've been using CubeSats to successfully educate students from mechanical, aerospace, space, and even naval architecture engineering disciplines. What we're currently trying to do is get people from electronics and computer sciences as well, because obviously there's a lot of this going on in satellites. Also, we've had a lot of interest from people from physics, geography, oceanography, and things like this, who are really quite interested to actually be able to see how a satellite is built or operated and things like this. So we have had projects, master's projects and bachelor's projects on this, and we'll have more next year and as time goes by. But what we also think of doing is running some PhD students and having them do part of the work for the CubeSat, simply because there could be a lot of research being done or some new technology developments that could be demonstrated in orbit, and that's a really good topic for a PhD. Well, so these are the objectives that we've been using to sell the idea of making a CubeSat to the university itself. But most of all, we want to have fun doing this, and there's a lot of amateurs and volunteers working on this, myself included. So it kind of ties into this amateur satellite theme. Right, so the first and foremost thing that we would like to do is build a CubeSat at the university. It doesn't matter what it does, but this is the primary goal. Also, we would like to take a couple pictures, or at least one picture, because if we don't take a picture, that is going to be pretty difficult to prove to people that we've actually gone to space and the thing that we made worked. So, yes, exactly. So it would be quite nice to take a photograph. The university itself has got quite a reputation in the space debris field, and one thing that is very difficult or virtually impossible to do at the time being is to predict when or where a piece of space debris is going to re-enter the atmosphere. And this is because we don't actually know much about the atmosphere, and we can simulate it, but we have no data to validate our simulation codes against. So actually, we've discovered that it will be quite simple and straightforward to generate some data like this using our CubeSat, which will tie in quite nicely with what people need to do, and what we have to do, and what the university does. So these are the primary objectives. The secondary ones, which are the ones that we may drop as time goes by, are dependent on a master's project that I was working on myself when I was doing my master's in that time. So the basic idea was to start building a CubeSat prototype at the university, just to develop it a bit further later on. We didn't have a lot of electronics or computer sciences experience. We had a lot of programming experience, which turned out to be very useful. But so we were looking for something really quite cheap and easy to handle, and that didn't require us to do a lot of soldering and things like this. So what we decided to do is try and adapt a smartphone, and at the time no smartphone had flown in space, and to build a CubeSat out of this. Turns out that NASA have done the same thing, and SARI have done the same thing, so it probably wasn't a very stupid idea whatsoever. But we haven't flown this into space as of yet. One thing that came out of this smartphone idea was that we actually had to use 3D printing, or we'd pay a load of money for manufacturing parts out of aluminium or something more space-worthy than plastic. But I'll come on to this. Okay, so if you're still with me, we're done with the boring part. So now the interesting bits. All right, so here's a smartphone that we've used, Galaxy Nexus. This is how it looks like when you take it apart. And this on the left is what we've actually put it together into. So our engineering model, if you like, of the CubeSat. It has the smartphone on top, then the GPS receiver, an SD card as well. What's missing on this picture is the radio equipment because it is still a work in progress, actually. And as a matter of fact, we're trying to get some radio amateurs from the university to try and help us build it properly so that we are sure that it's going to work, because we simply didn't have enough expertise in this particular area of building RF boards. So first lesson that we learned is that if you decide to reproduce something like this, or really look at this website, iFixit, before you buy any phone whatsoever, or even start remotely thinking of which one to choose. Simply because the varieties are fantastic. And some phones can be disassembled quite nicely and into nice parts that actually fit in the CubeSat envelope, and others are just horrible. And there's no way on earth you can fit them into a CubeSat. And there's no way you can actually cut them into halves, split them. And so, yeah, just be sure that you look at something before you spend money on it. All right, so here's more about how it actually looks like on an architecture level. So what we have on the left is a smartphone board, which is one compact electronic board, and it's all-inclusive. So you've got the two parts of the Galaxy Nexus there. An interface board. Since we only have one micro USB port on this phone, we have to use this in order to have communications with all external devices, so radios, GPS, and so on and so forth. So we need some interface to change from USB bus to I2C or something like this. On this particular board, we also have a GPS receiver. The one that we have right now is only suitable for balloon flight, but we're working hard, or actually we are in touch with a manufacturer to remove some of the restrictions to actually make it suitable for space flight. And we know this is possible because we've been in touch with some people that have used the same GPS receiver in space, and that's the idea. And we use a radio as well, which we connect to the phone via USB, which is quite nice and simple. And actually, if you look at this, it really is not that complicated. The things which are missing right now is the power system, but this is primarily going to be worked on this year when the new students start working on this. So this is hopefully going to come. But you never know about when you've got students working on it. Anyways. And here's another thing that is both a blessing and a curse of using a smartphone to make a CubeSat. So it is nice and compact. It comes with a lot of hardware in it already, and you don't have to worry about it. You don't have to solder things. You don't have to write really low-level assembly software. It's done for you. When you buy it, it's ready to go. But this is also a curse, simply because if you had to, you cannot add an external USB port, just an additional one, just to have some redundancy. It's not going to happen. And this is a bit of a problem because, if the micro USB port fails, your whole spacecraft may have failed. So it's really quite a trade-off. It can get your spacecraft into space quite quickly and easily, but you are risking a lot whilst doing so. All right, so that was the difficult part, the hardware. When it comes to software, it is absolutely amazing. I mean, I actually was writing the software for this, and to go from absolutely no experience in this kind of software design, or even the language in which you write, so Java, to actually writing a working piece of software for the balloon flight, because we flew it on a balloon, it takes about 2 months, working evenings and weekends. So it is absolutely amazing. And when you look at the architecture of it, it is really quite fantastic. So you write most of the stuff in Java, and then just a little bit of stuff in C++. You have to recompile the Linux kernel once, which is a bit of a tricky game, but you can do it, I suppose. And that's it. There's no low-level programming, nor assembly language, no writing schedulers, things like this. It's just all really nice and top-level Java that's fantastically easy to write in. All right, just to recap. Smartphones are nice for CubeSats because they are cheap. And they have a lot of software that comes in them and hardware. A lot of help, fantastic resources, lots of open source programs that you can actually use to your advantage and change them slightly. fantastic array of sensors ranging from accelerometers, gyroscopes, magnetometers, or even Geiger counters on some phones nowadays. You can do a lot of science with them, actually. It's quite surprising. Or you can use them just for housekeeping purposes, so to know attitude of the satellite, know whether it's in light or whether it isn't, temperatures, things like this. Really, really nice. Yeah, but the thing that I've been mentioning is that they're really quite difficult to modify the hardware of the phone. So something that you have to be wary of and cope with somehow. I don't fully know how, but and it's, quite frankly, you also need to hope that it simply is not going to fail some parts of it, because there is no way you can implement extra redundancy into the phone itself, unless you use two phones, but that makes the whole system really complicated. So one more disadvantage is that they are quite susceptible to radiation, but to be perfectly honest, anything that's designed for terrestrial operations is susceptible to radiation damage. So electronics, memory banks, an ARM processor, as far as I understand, could fail due to a single event upset. So this doesn't make phones any different to any other alternatives that you might have, unless you're willing to spend tens of thousands for a space qualified and hardened computer. Again, same thing as other things. They can fail due to vibration or launch accelerations and things like this, or capacitors may explode due to the vacuum that you expose them into, and there may be some gas trapped inside that's going to just make the whole thing explode. But again, that's nothing new. One thing that we've learned actually from our colleagues from SARI is that phones are quite susceptible to temperature as well. And actually, some of them may switch off when they get too hot or too cold by themselves. So this is a very important thing to pay attention to, because you really need to keep the phone in the right temperature range at all times, or else it's just going to switch itself off and presumably not come back on unless you get it to the right temperature. So some thermal modeling and tests are really crucial for this. All right, so that is it. Thanks all for your attention. I hope you've enjoyed it. And I don't actually know how long I've taken, so I don't know if we've got time for questions.
Yeah, I think you were scheduled for half an hour or so, and we've certainly got a good 10 minutes.
Okay, I thought it was 15 minutes, but anyway.
15? Okay, in that case, you're spot on. Brilliant. And you've paid attention.
All right, so wonderful. No questions.
So hold on just a second. We'll see if we've got some questions here. I'm sure any university team in the UK must generate some questions from within the UK. After all, these people are our space engineers of the future. So do we have any questions from within the room? Thank you.
Bearing in mind your comments about the performance of the phone, temperature and capacitors exploding and things, have you tried putting any in thermovac chambers and testing them?
Right, we've tested in low temperatures, and it went through okay. What we're going to do actually in August sometime is to put it in a vacuum chamber and to see if it's going to fail or not. Most likely it won't, because phones of the same brand, Samsung's, have been flown in space already. I don't know with how much modifications, and that's the only thing that may make it fail, but hopefully it's going to be okay.
Okay. Any ideas on the maximum minimum range of the phones in normal
maximum
use?
Minimum range of
before they fail, temperature.
Oh, temperature. Well, they won't fail. They will just switch themselves off. So that's it. And it's -10 plus 30, 40 degrees.
Okay, so you stand some dangers of getting into those limits, don't you, in space? Anybody else with questions? Yes, we have one over here.
Hi. I can't remember if it was in the slide or not. I was just wondering if you were considering maybe putting any propulsion on there in the form of...
Putting what, sorry?
Some propulsion, perhaps? Because I seem to remember Southampton and your friends at Mars Space have been developing some rather neat little pulse plasma thrusters. We've given it a go. We haven't tried them yet, though. So.
All right. So, you see, the problem is that you're from SARI, as far as I understand, yes. So, we've never built a satellite at Southampton, a fully functional one. So it's quite a challenge in itself. Just to put a radio beacon in space would be quite challenging, and is going to be quite challenging. So adding extra experiments to it is, make it even more difficult, if you like. But the thing is that once we have a platform that we're happy with, and we've flight proof on it, then there's no limit as to what we could potentially fly on it. And one of the reasons we wanted to make it cheap is to be able to fly different missions. So say, electric propulsion or something from geography. We've got a lot of interest from physics. So having a CubeSat platform that we could just be box standard and just plug different experiments into would be fantastic. And you can presumably do it with a phone because, you just have a USB bus, and then you just plug it in, put it into the hardware envelope, and reconfigure the software slightly, which, as I said, doesn't take a lot of time, and you're off.
The first step for a
Yes.
Okay, well, in that case, I'd like to say thank you very much to Aleksander for making the journey up today to speak to us.
For Southampton, it's just 2 hours, so it's not as big a journey.
It's further than I've come, so it's a long-distance trip for me. Before we go for the lunch break, Kieran has some housekeeping announcements, and after that,